All right, so I am live streaming to YouTube right now. Can somebody go on there and check to make sure the audio is working? What button is the brightness button? You mean on the Chromebook? I don't know. You all can go on the live stream on YouTube and see if the audio is working on that. Yes, Leo. All right, thanks, Joanna. Okay. All right, so I'm gonna go ahead and take attendance. Adrian's here. Brian is not. Chad's here. Emma's here. India's here. Hans is here. NBA. Iverson. James. Joanna. Kayla is not. Kadeem is not. Leo's here. Louise. Shayla. Stuart. Tasme. Treyon. Trinity is not. And Uriel's here. All right. So if Brian, Kayla, Kadeem, or Trinity come in, let me know. Alrighty. So last time, what we talked about was, let's see. Last time we were talking about what happened on Wednesday. So what I want to do is I want to go through an example and discuss how we can figure out what the coefficient of friction is when we're given certain things. Okay. So in this example, I've got, let me chat up. So in this example, I've got 50 kilograms that I'm going to be pushing. And what I want you guys to notice is that, so I'm applying 50 newtons and the object is not moving. My velocity is not changing. So if there's no change in velocity, there's no change in my state of motion because I was originally at rest. So I'm applying 50 newtons and my velocity is not changing. So therefore my state of motion is not changing. If that's the case, that means that the force that I'm applying is being canceled out by the force created by friction. And if they cancel each other out, that means that my net force is equal to 0. Somebody else just come in. Okay. Give me 1 second. Switch back. All right. So Kayla, Trinity, and Brian. If any of those guys come in, let me know. All right. Let me switch back. Okay. So if I apply 100 newtons, notice that it's still not moving. The speed's not changing. My friction force is the same as my applied force, but it's in the opposite direction. So applied force is to the right, friction force is to the left. It's going to oppose the tendency for, like, if the object was going to move, it was going to move to the right. So friction is going to be moving in the opposite direction. It's going to want to oppose the motion. So I can go all the way up to 200 newtons. Now, what I want you guys to do is to pay close attention to this right here, this 200 newtons for the friction force. Now, when I give you guys a problem, I'm not going to give you what the frictional force is. I'm going to give you the applied force, and I'm going to give you the mass of the object. And that's all you're going to need to solve this type of problem. I wish there was a way to hide what the frictional force is, but this is more of a simulation instead of like doing actual problems. But what I want you guys to recognize or to observe is watch what the value of the frictional force does if I just apply 1 more Newton. Okay, so I've applied 200 Newtons, but there's going to be a is the box glued to the ground? No, it's just a lot of friction. So notice that the friction is all the way over here at almost at the lots of friction. So if I apply 1 more Newton, observe what happens to this. So what happened? So I'll turn it off, wait for it to stop. So I'm going to go back up to 200 Newtons, right? I'm already pushing with 200, but the threshold that friction is holding onto this box, so it's right on the cusp of starting to move. And if I apply 1 more Newton, all right, I see that Brian is now here. So bear with me, make sure I get him. And switch back. All right, so this is right at the max, that the maximum amount of force that friction can apply to hold that box stationary. Okay. Once it breaches that threshold, once it goes past 200 Newtons, the type of friction that's being applied goes from static friction or stationary friction into kinetic friction or friction of motion. And this does a really good job of demonstrating the fact that the static friction is going to be always higher than the kinetic friction. So watch what happens to the number. I'm going to do it again. So if I start applying 201 Newtons, watch the frictional force drop dramatically. So it went from 200 and it dropped down to 150. So now this is the kinetic friction that's being applied because it's moving. And notice that I'm still accelerating. So even if I drop down to 150, so now my speed is remaining constant. Like it's no longer speeding up or slowing down. But when I was applying 150 Newtons before, it wasn't moving. So this does a really good job of demonstrating the difference between static and kinetic friction. So what the objective is for today is to figure out what the coefficient of static friction is for this situation. Okay. So I'm going to wait for it to stop. And this is going to be a type of problem that you will see on an assessment. So figuring out what the coefficient of static friction is. Cool. So the situation that we're going to be analyzing today is this right here. So we're going to be applying 200 Newtons of force to a box that has a mass of 50 kilograms. Cool. And what the goal is to figure out what the coefficient of static friction is. Now, just as a reminder, the coefficient of friction is mu. Okay, so mu is the Greek symbol that we use to represent how frictiony a surface is. So something is smooth and it's easy to glide something across or to slide something across, it's going to have a low coefficient of friction. If it's more rough and it's more difficult to slide something across it or to slide an object across it, then it's going to have a higher coefficient of friction. So these coefficients of friction are derived by a ratio. So there's not going to be any kind of units associated with it. And when we find out what these values are, they're always going to be greater than 0, but also less than 1. So that's what the bounds are. Greater than 0, but less than 1. So if something has a high frictional value or a high coefficient of friction, it's going to be 0.8, 0.9. Those are going to be very frictioning. If something is very slick and very smooth, it's going to have a low coefficient of friction, or like 0.0 or 0.1, 0.2. Those are very slick and smooth stuff, item or surfaces. Cool. And what I also want to point out is that this coefficient of friction that we're talking about is referring to the coefficient of friction of the surface that it's sliding across, not of the object. Cool. Any questions so far? All right. So this is our initial situation. So we've got a box, and we need to figure out what forces are acting on this box. So based on this simulation, would you guys agree that there are forces acting on this box? Yeah. So obviously it's going to be the applied force. And we can see due to the simulation that we are applying a force and it's not moving, it's not changing its state of motion. So we know that there's a force that's equal yet opposite, and that's in this case going to be the frictional force. When I give you guys a problem, I'm not going to show you what the forces are. I will tell you what they are, but I'm not going to give you a diagram representing that. That makes sense. The reason why is because it'll give you too much information, and the problem will just be too easy. But in general, these types of problems are pretty simple. So, even more elementary than that, we know that this box obviously has a mass, right? And if something has mass and it's on Earth, we know that what is acting on it? Gravity. Good. So if we have gravity acting on the box, then we need to represent the force due to gravity. And in this case, the force due to gravity is acting downwards. So this is going to be the force due to gravity. Cool. Now, according to this simulation, we can observe that the box is not slowly sinking into the ground. It's not somehow magically floating above the ground, like moving upwards. So in that kind of situation, I know that the forces in the y-axis cancel each other out. So I know I can observe that gravity is affecting the box. So that means that there must be an equal yet opposite force counteracting the force due to gravity to keep it from being sunken in or sucked into the ground. So that means that the force has to be coming from the surface. Okay. So the surface provides a force called the normal force. And that normal force, get out of there. The normal force will be acting in the opposite direction of the force due to gravity. And this is produced by the surface. So that's the normal force. Cool. And then I have to represent the force that I'm applying. So this would be the force push. Whoops. Stupid sticky keys. So this is force push. And then the force due to gravity is going to be in the opposite direction. Or sorry, the force due to static friction. I don't know why it keeps doing this. Okay, so this is going to be the force due to friction, and this is going to be more specifically the static friction. All right, is there any questions about that so far? All right. So we know that in both the x-axis and in the y-axis that all the forces in those respective axes cancel each other out. So I know that do this right. I'm going to slide this over just a tad. So I'm trying to make this make it fit in the size of a normal 8.5 by 11. So I can post this online for you guys. So the net force, so F net in the x-axis, I know that the net force is 0 because it's not moving horizontally. So all the forces in the x-axis cancel out. So the only forces that are in the x-axis are going to be force push and the force due to friction, and that's going to be the static friction. Cool. And I know that when I add those two forces up, they must equal 0. My net force in the y-axis, it's going to be the same process, but in the y-axis, I have the force due to gravity, and then I have the normal force. Everybody cool with that? So net force in the x-axis, I'm just adding these two together. And then same thing with the y, I'm adding these two together. Okay. Now, my objective is, like, what I need to find is mu sub s. Okay, so that's my coefficient of static friction. Now, right now, I don't have mu sub s in any of my equations. There's one more equation that's dealing with the force due to friction. So force due to friction, more specifically the static friction, that's going to be equal to mu sub s multiplied by the normal force. So these are the three main equations that we're going to be using. So these ones we came up with just by looking at the diagram. This last one, dealing with the force due to friction, this is one that I would definitely recommend writing down. So the force due to static friction is mu sub s times the normal force. And then if we were trying to figure out what the coefficient of kinetic friction, that would be, now this is just a side note, the force due to kinetic friction, mu sub k times the normal force. Okay, but that's not one that we're going to use for this problem. All right. So what do we know? So in the problem, I can see that my mass is 50 kilograms. I know that my force push is 200 newtons. And since we're dealing with gravity in this, we're dealing with the force due to gravity, we can always put in the acceleration due to gravity. So the acceleration due to gravity in my class, just to make the arithmetic easy, we're going to use 10 instead of the 9.81. So that's going to be meters per second squared because it is an acceleration due to gravity. So those are the knowns. And what I want to do now is I want to find an expression that has mu sub s on one side and then equals something that's comprised of just my knowns. Cool. So that's what I want for the equations part. Now, these equations here, the variable that I want is right there. And I can use all three of these to kind of manipulate what I can do and kind of distill it into just some sort of combination of these. And there's one more equation. I apologize. The force due to gravity. And let me move these guys down just a little bit. Okay, it's a little bit better. So we also know that the force due to gravity is just mass times the acceleration due to gravity. Cool. All right. So what we're going to do is we're going to start off using this third equation right here. Okay. So that one is going to be the force due to friction static is equal to mu sub s times the normal force. Now, I want that to be by itself. So in order to get that by itself, I have to divide both sides by the normal force. So it cancels out on that side. And then this leads to an expression for mu sub s equals the force due to friction static over my normal force. Any questions about that? Okay. Now, am I given my static friction force or my normal force? Now, you guys might be thinking that in this diagram or in this simulation, I do know the frictional force, but that's not going to be given to you in a problem. All right, so I'm not outright like it is not a known given to you in the problem statement. Okay, so in this example that we're writing down, we're going to assume that we don't know what the frictional force is. Cool. But if I look at my equations up here, I know that the friction force, if I add that to my force push, if I add those together, it's going to have to equal 0. So what it ends up being is force push is just the opposite or the negative of the force due to friction static. Or vice versa, the force due to static friction is just going to be the opposite of force push. Cool. So that's derived from this. Do I need to go into more detail about that? Or you guys? Okay. I know Kadim's doing a lot of talking, which I don't mind. I just want to make sure that if somebody does need me to go over it, I do. Okay. So I'm going to do the same thing with the normal force. because when I add that to the force due to gravity, it has to equal 0. So I know that the normal force and the force due to gravity are equal in magnitude, but opposite in sign. So I get minus force due to gravity. Cool. So we're getting there. So we've got the negatives canceling out. Force push, in my given force push, I do indeed have a value for that. So that one's good to go. But force due to gravity, I'm not given a value for that. But luckily, I have an expression for force due to gravity, and that's just m times g. So the last algebraic step that we're going to do, so force push over, and then the force due to gravity, yes. So that's why I'm kind of making it in the form of like an 8.5 by 11 sheet of paper. So that way I can upload this document along with the video that's being live streamed to YouTube right now. All right, and then the force due to gravity gets replaced by mass times gravity. Cool. So I just substituted this right here. So now, and I know I'm going a little bit quick today. I apologize about that. So I am given force push. So that's given right here. I am given the mass. It's right there. And I'm given the acceleration due to gravity. So just like in the problems that we've done in the past, on the left side, I've got the variable that I'm solving for. And on the right side, all of these are located in my nodes box. So now I'm allowed to plug in. All right, so mu sub s is equal to force push over mass times gravity. So my force push is 200 newtons. Mass is 50 kilograms. And then my acceleration due to gravity is going to be 10 meters over seconds squared. So this is going to be 200 over 500, and that's going to be newtons over, and then a kilogram times meter over second squared. That's also a newton. So like I mentioned before, coefficients of friction, whether it be static or kinetic, are going to cancel out the units, so that they're essentially unitless. So newtons over newtons goes away. So 200 divided by 500 is going to be 0.4. So the answer for the coefficient of static friction is 0.4 for this problem. Sorry for moving it all around. All right, any questions? I'm assuming you guys are trying to write all this down. Okay. So in this situation, instead of figuring out the coefficient of static friction, if I wanted to figure out the coefficient of kinetic friction, what would change? Like, how would this be modified? What would be different if I was looking for the coefficient of kinetic friction versus the static friction? Would the mass change? What, Kadeem? Okay, I took the FFS as something else. I thought it was the shorthand for blank sake. So so it would no longer be the force due to static friction. It would now be the force due to kinetic friction. So the difference is that the mass wouldn't change. Acceleration due to gravity obviously wouldn't change. So the force push, if I go back to the demonstration, so once I go up to 201 newtons, I've now passed over the threshold for static friction. But notice that I was at 200 and it wasn't moving. But now, what I can do in order to make this sum of the forces go back down to zero, I now only have to apply 150 newtons. So, for to figure out what the coefficient of the maximum amount of pushing force that I need to apply in order for the frictional force to be maxed out. If I go up to 151, I will have now overcome kinetic friction because I will start to accelerate. So if I go to 151, you'll notice that I now have a sum of the forces equal to 1. So if you look at this, it's going to go up, but it's going to be very slow. So now it's 18.1, and then it'll be 18.2 in a second, right there. So if I go back down to 150, the maximum amount of force that I can apply to have the kinetic friction be maxed out would be 150 newtons. Is everybody tracking? So the max that static friction can apply was 200 newtons. And then for kinetic friction, the maximum that kinetic friction can apply is 150 newtons. So if we were trying to figure this out, trying to figure out what the coefficient of kinetic friction is, the maximum, the amount of pushing force would instead of 200, it would now be 150. Does that make sense? So I would do the exact same deal, but since we've already done this algebra, and the only difference between this equation for static friction and the one for kinetic friction is that I just put a K instead of an S. Does that make sense? So in other words, the only difference is the mu sub S, we had the force due or force push over mass times gravity. The force due to kinetic friction is going to be the same thing. But in this case, in the one that we just did, it was 200. But in the new one, force push was 150. So this would be the force push with kinetic, and that's 150. And this is the force push with static. That's 200. So we can very quickly figure out what the coefficient of kinetic friction is. So mass of 50, and then the acceleration due to gravity. So that's going to be 150 over 500. And I think it's 0.35. 0.3. So the coefficient of kinetic friction is equal to 0.3. And from the example that we just did, the coefficient of static friction is 0.4. Cool. Anybody have any questions? All right. So, got through that a lot quicker than I expected. Um, cool. Okay. Um, yeah, that's all I had for you guys. I was not expecting to go through that quickly. All right. So I'm going to go ahead and end the live stream. If anybody's watching that, I'm going to go ahead and cut that